So today is a lecture on a very general technique that covers many problems that come up in parallel computing, and it's load balancing. So let me recall some motivation for load balancing. Some of the problems that we've talked about this semester have been very regular. Every processor naturally gets an equal amount of work to do, but lots of interesting problems are not that way. So in particular, sparse matrix vector multiply, or sparse matrix, depending on how you the number of non-zeros per row, you can get a lot of different work for different processors. And so we talked about how to do that particular problem. We talked about graph partitioning at great length. I'm going to call that a static load balancing technique because you know everything before the problem starts. The dynamic case, which is what this lecture is about, is where you don't know the costs until the problem runs. And so there's a big spectrum of different pieces of information that could influence how you want to do load balancing. And so there's lots of different techniques, and there's no one size fits all, which is why there's a whole lecture on all the different approaches. So the task costs could vary from they're all the same to they have some probability distribution that you know with some mean and standard deviation to you have absolutely no idea until you actually create the task. You may know at the beginning of the task creation, or you may not know until the end. If you're doing, searching a chessboard for the next move, you may not know until you've searched a big chunk of the tree and the thing returns how long did it actually take to run that task. The dependencies, similarly, everything can be embarrassingly parallel and independent. That's the case people have studied the most because it's the easiest. But they're also, or you may know it's a tree, or you may not know until the end as tasks are created and create subtasks that depend on them, what you need to do the balancing. And finally, the locality can vary. Again, embarrassingly parallel, nobody depends on anybody else is the easiest thing to do. But there are a lot of problems where a chunk of data is sent from one processor to another, and if you put those on different processors, it'll cost more. And so you may have this trade-off between locality and balance. So there's going to be a spectrum of solutions. We talked about the static case with graph partitioning at some length. I won't do that again. That's where you know everything ahead of time, and you can spend a whole bunch of time if you want to figure it out. And then it's sort of this spectrum up to where you don't know anything until it's over. Semi-static, you know a little bit before you get started. And dynamic, it could be little or no information before you start. But there's another sort of metric, which is that it may be that you don't know, the problem starts, you measure some statistics, you figure out how to balance it, and suddenly the program goes into a different phase, and everything becomes unbalanced again because you've hit a different part of the program. And so how fast does that occur? Does it occur gradually or abruptly, and how often? And so I'm going to give you a survey of a bunch of solutions, how each one works. In some cases, in the simplest cases, people have nice theory that says that randomized algorithms work well, so I'll just tell you what that theory says. And then there's a lot of software. People have built many, many tools, so you should, again, use the tools if they're available and good for you. So let me just give you a little survey here. So why is your parallel code inefficient? We started that discussion this morning about homework number 3, but it could be poor single processor performance. And the matrix multiply homework was an example. Chasing shared pointers when they're local pointers in UPC was another example. There may be too much parallelism overhead because thread creation costs a bunch of stuff. You don't want to do a spawn for every floating point add. Synchronization, communication too, and then load imbalance, which is what we're going to spend most of our time on. Different amounts of work across the processors, but it could also be that the machine is not homogeneous. It could be the tasks are the same, but different parts of the machine are running at different speeds. And this was originally considered and invented when people were taking all of the different computers in their lab, gluing them together over some local area network. There were old machines that were slow, new machines that were fast, and people wanted to use the machines in their lab as well as possible. But now, of course, you not only have CPUs and GPUs, you have failures because these machines are getting so big, so something may be slow because something is going wrong in it, or it could be shared. Somebody is using a process, and some machines are idle and some are not. So the question is, how do you recognize that it's the load imbalance that's the problem? And we had a whole lecture on that. There are a bunch of tools. And so let me just show you a picture, which is the output of one of those tools. And so this is data that was collected by a tool called TAU, T-A-U, which is one of those standard tools that they run at NERSC. And this pretty picture, which is a little hard to see, was visualized by a tool called Vampire. And so what it does is it inserts timers into the MPI code, and it has a timeline for processors. So there's the timeline of what processors 0, 1, 2, 3 are doing. It's color-coded by which subroutine is executing during each particular phase. So there's the yellow subroutine, the red subroutine, and I guess the Beatles are executing during that one. And then there's black lines where connecting every communication. So if there's a black line from processor 0 down to 3, that indicates that there's some communication that went on. Now, that's a little hard to read, so here's the same picture without any of the black lines. And now you can just see what each subroutine is doing, and this one is pretty well load balanced. Otherwise, there'd be a bunch of times labeled idle. There aren't any here, and so they all ended about the same time. So we could have seen if there were idle time here. And so that would tell you about computation load imbalance. And then there's one more little window, which is the communication imbalance. So this is a little matrix with one row and column for every processor, and the number there tells you how many words were sent from processor I to processor J. And so we could look at this and see that it's a little hard to read, and maybe there are 18 megabytes sent from one processor to another, and if they're all about the same, it's load balanced. So these are tools that are available to help you realize that there's a problem and that you might need to use some of the dynamic load balancing tools. Okay. So just to review graph partitioning in one slide, again, this is a static case. So I have a graph where the nodes represent the tasks, the edges represent how much communication has to go between them. There's a weight associated with each node which says how much work are you actually doing. In the simplest case is that they're all unit work, and each edge may also have a weight, which is how much communication is required to go from one to the other. And so what we talked about was how do you divide up your graph into p pieces so that everybody has an equal number of nodes, an equal sum of node weights, and that you minimize the communication between them. And we had lots and lots of tools for that. Now, this can actually also be used in the dynamic load balancing case, but it may be that you have to wait until runtime where you can actually get the estimates of all the nodes and edges. And but you'd only want to use this if you're going to run the program for a long time and the costs of the tasks do not change very much. So for example, there's a tool I'll talk about later in the lecture called Charm++, where this is an option where it assumes that you're doing the same task kind of over and over again. They're going to have constant statistics run times, and if you want, it'll let you do graph partitioning in order to do that. But that's sort of a simple case. So let me give you an overview of the design space of all the way tasks and costs can vary, and that'll motivate all the different kind of tools I talk about. So the task costs, as I said, the simplest case, they're all the same. But if not, when do you know the tasks? That's important. You may know it before you start. That might be sparse matrix vector multiply. You may know it when the task is created, or it may be only when the task ends. You're doing some complicated search, and it's not until the thing returns that you know how long it took. The dependencies can range from they can run in any order you like, it's all embarrassingly parallel, to they have dependencies. And again, the question is, when do you know the dependencies? You may know them before starting. Dense linear algebra, I'm going to know ahead of time which block has to be done before which other block, and people still do dynamic load balancing for linear algebra. Or when the task is created, or again, when the task ends and it spawns some children that it's going to depend on. There's also the possibility that when one task finishes, it can kill another task. And that would be the case if you're doing search in a tree, and maybe it's a game search, and it's a chessboard, and you're going down one path and you discover there's a way to checkmate your opponent. What you want to do is when you return is turn off all the other tasks. You don't have to continue searching them. You found the right answer. And there are a lot of examples like that where you're searching a tree and you found a good answer and you can turn off all the other tasks. That will impact the load balancing too. And then there's locality, which is that are all these tasks, if they share something, it's important to schedule them on the same processor. That may, of course, mean that it's hard to balance the load if you want a bunch of processors scheduled and this task scheduled in the same processor, or it's okay to have them be scheduled in different places, and when do you know that? So let me just draw some pictures here to show you what these look like. So here's the task cost spectrum in order from the easiest case. They're all the same, and you want to put them into P bins. And down to the harder case when the tasks are different. Now, in this case, I think I mentioned this before, if the tasks are all different sizes, and even if you only have 2 bins, if your goal is to put these n items into the 2 bins so that they come out as even as possible, that's NP hard. So even just solving that simple problem, we have to resort to heuristics because it's too expensive to get the right answer. And so we'll have some heuristics about that. And then finally, you don't know the task costs until after execution. And that would occur in circuit simulation because the circuit turns on, it causes something to happen. The next piece of the circuit may be cheap or not. Search and even global climate modeling. And in that case, you're simulating a part of the atmosphere, a storm occurs, that's hard to predict. You get a bunch of clouds, the clouds take extra time to simulate, and so there you get a load imbalance. So here's what the task dependency spectrum looks like. Again, sorted from easy to hard. Dependence free, so you could think of matrix multiply as kind of being in this case if we don't worry about all the adds that occur at the end. The next case is that there's a predictable structure. So here's a wave front. These three are independent, then these three, then these three. Or you can have an out tree followed by an in tree. That's easy to describe. Or you can have a general DAG, but you're given the DAG somehow. So it could be the DAG that comes from a standard linear algebra operation like dense matrix factorization, let's say dense Cilk. And then the hardest is when the structure changes dynamically. And that can also occur even in regular old linear algebra. So let's compare sparse Cilk with sparse Gaussian elimination. What's the difference that could cause this to have dynamic scheduling required and this having more static? And the answer is pivoting. You don't know until you get to a column of the matrix which row you want to pivot into the diagonal. That's going to affect how it fills in, which task gets generated later. And so sparse LU can be more complicated than sparse Cilk, where you can just pretty much go down the diagonal. So, and then of course, once you throw in games and search and all of that, it becomes very hard. So, and then there's the task locality spectrum. And again, in order from the tasks once created, do not communicate. It's all embarrassingly parallel. You can schedule them wherever you want. The next harder thing would be there's some regular pattern where they're talking to their nearest neighbors on a torus. We've seen lots of examples like that. Or there's a PDE solver, so there's a mesh. We know it. And then where it's completely unpredictable, some discrete event simulation, and you don't know until it happens. So here's the spectrum of solutions that we're going to talk about. Static scheduling, we've been there, done that. That's the graph partitioning problem. Now, it turns out that you still might use the dynamic approach, even if you could, in principle, do static scheduling ahead of time. And we'll see that later. In the case of dense linear algebra, people do dynamic scheduling in dense linear algebra, even though it seems so totally regular, just because processors can run at slightly different speeds, and you don't want them to wait for one another. And so how big is the DAG, the directed acyclic graph connecting all the tasks in linear algebra? If I have an n by n matrix, and I do b by b blocks, each little task, b by b block is a task, how many tasks are there? It's n divided by b cubed, right? So the number of tasks is growing cubically, and that's too big a task, a DAG, to write down. People started doing it that way. It turned out to be too big, and they've switched to doing dynamic load balancing even for dense linear algebra. So even though it seems static, you might use dynamic cases. In semi-static, you may know it, the information may change slowly. So here's an example. Suppose we've divided up my graph in a reasonable way, and then it changes slightly. How do I want to just change the balance a little bit and rebalance it to make it good? We actually had an algorithm for that when we talked about graph partitioning. It was called Kernighan-Lin. What did that do? It took a partition of a graph, and it moved a few items from left to right across the border to make it a little bit better. And so we could run that algorithm too to do semi-static scheduling. If we don't have to do that very often, that's a pretty cheap thing to do. And then there's the completely dynamic stuff, which is what we're going to talk about today. So let me just talk a little bit about search algorithms. I mentioned chess, but they're chess games, but there's many others. And then there are going to be sort of two different approaches, one depending on which is more suited for a shared memory machine, where I can sort of afford to have one central queue which keeps track of all the tasks, which everybody can talk to, and get the information from there. But that has limits in scaling, obviously, if I have a central depository of all the work. And then there's the distributed case where I can't afford to do that, and I have to do typically things that are more randomized, sort of throw random work to random processors and hope for the best. And there's some theory about that I'll talk about too. But let me talk about search. So here's some examples of search problems that, depending on what department you're from, you can identify with. They're going to be expensive. How do I lay out chunks of silicon on VLSI chips? Here's the adder, here's the cache, here's a multiplier. So I can use all the area and minimize all the wire lengths between them where things travel. That's an expensive search problem as I move stuff around. Robot motion planning, there you have something, a robot who's moving in a dynamic environment, and depending on what's moving around the robot, it has to change its plans. Games, speech processing, and where I'm trying to line up genes from one sequence to another, that's also a search problem. And so these are all examples of where we're going to do it dynamically. So let me say a little bit more about what a tree search looks like and why it's going to be dynamic. And typically in a tree search, the tree is going to unfold dynamically. I don't know what it all looks like until I get there, because at this point, this node may have children, but I may decide that there's no point in searching beyond that node. It's going to end. So here's the root. It's not a terminal node. I have to search the children. So it generates, let's say, 2 children. This one, it'll stop there because it's been checkmated, and there's no need to go any farther. It won't search any more children there. This one, there are more moves that go on. And finally, at the bottom here, every node is either I've lost, or I have a way to win, or I have a high probability of winning. And so at this point, this particular node will perhaps stop, and I don't even have to search that one if I'm lucky. So there are 2 different ways to search trees, and I think this is sort of well-known basic computer science, but let me just remind people that there's depth-first search and there's breadth-first search. And this is a review of what the code does, but let me just say it in a few words. In depth-first search, you start at the root, and you keep following children down until you get to the bottom, until you get to a leaf, and you can't go any further. Then you back up until there's a child you haven't searched, and so it always goes as far down as possible at a time. That is done with a stack, where you take the vertex that you're searching, and you put it on the stack, and then if there's a child you haven't searched, you push it on the stack, and when you're done, you pop them off the stack. That's the data structure that makes it work. The alternative, and we did talk about that in an earlier lecture, it's breadth-first search, where you search all your children, and then all the grandchildren, and then all the great-grandchildren in that order. And so that's yet a different way. And there's obviously a lot more parallelism possible because if my tree spreads out quickly, I have lots of children, lots of grandchildren, even more great-grandchildren. But they're both going to be important to do. Sometimes I'm still going to want to do depth-first search. So let's talk about sequential search, in particular the depth-first variety. The simplest way that people organize it is by just backtracking. I go down to the bottom where I decide it's not worth going any farther. Then I back up and search, the brother or the sister or however far up I have to go. And there's a technique called branch and bound search. That is one of the 13 patterns that has been mentioned many times in the course of the semester. So what I'm going to do as I search is I keep track of the best solution I have found so far. And when I back up, I'm not going to bother searching any subtree where I can't beat that lower bound. So somehow I get to a vertex in the tree and I say, every possible solution from here on out, I can't win more than $1. And if I get to another place where I can't win more than 50 cents, I'm not going to bother searching the 50-cent subtree because I know I can already win $1. So that's called, I'm going to sort of just cut off subtrees when that happens. And then there's breadth-first search, as I mentioned. That sort of search children, grandchildren, great-grandchildren. But there's something in between, which is called iterative deepening. And what that does is that you say, I'm going to pick a depth D, a generation of removal of depth D. I'll do depth-first search down to that depth, search all of that, but then I will stop at that depth, and then I'll start again at that depth and do depth-first search again. So it's sort of a mixture of depth and breadth, and people have used both. So the question is, so this is sequential, how do I map this to be parallel? And so let me try the simple backtracking approach, where I go as deep as I can and then come back up. So let's suppose I had 2 processors, and here's my tree, and again, I don't know the tree until I traverse it. So one processor starts at the root. The root has 2 children. The root assigns the purple processor to, this subtree, the left subtree to the purple processor, and the blue processor keeps this one. And so the blue keeps on searching, the purple keeps on searching, and you can see, since it doesn't know what the trees look like, it's completely load imbalanced. And here is a similar situation. Suppose I have 4 processors. The root, the purple processor, starts here. He has 2 children, so he says, okay, the yellow and the green processor do that one. The purple and the blue processor do that subtree, and it keeps splitting off until in this case, after 2 levels, 1 processor is assigned every subtree. And again, the load balance can be awful. So we should do better than this. This would be a natural thing to do. So the first approach, which is suitable for shared memory machines, is centralized scheduling. And in that case, you simply have one central location where you keep a list of all the tasks that you want to have done. It has a task queue, and that's sort of the master, and everybody else is a worker, or a master slave is another name for this. And so whenever a worker has finished a task, it goes to the central location and says, what's the next thing I should do? Clearly, this is a very load-balanced thing to do. Everybody goes to the one place, and many offices are organized this way for obvious reasons. But you can see that there's several failure modes, several ways this can fail. So for one thing, if the chunks that this guy doles out to all the workers are too large, he's not going to keep everybody busy. And if they're too small, if it's a few multiplies and adds, then he's going to be a serial bottleneck. Everybody's going to be lined up to get a little bit of work to do, and it'll be load balanced, but you'll spend all your time touching there. So the question is, what is the right size of the tasks to dole out? And much theory and many algorithms have been invented to choose that. So I'm going to give you kind of a tour of how people choose the task sizes to dole out. And so this was applied first to scheduling loops, where I have a loop from 1 to n, and each inner loop iteration is one of those tasks. And this is, in the literature, this has been called self-scheduling, so I'll just use that terminology, where you have a centralized task queue. And so you can think of a task as a range of indices. I loop from 1 to n, so one task may be 1 to 3, the next one is 4 to 7. How do I decide what size chunks to do out? I'm going to assume it's all independent, so there's no dependencies. I can do it in any order I want. And indeed, this was originally invented in the compiler community when people were doing, figuring out how to generate code for parallel machines. So let me talk about the different variations people have invented for picking the sizes of the tasks. And as I said, you don't want to pick one loop iteration. It's too small. So I'm going to choose a chunk of tasks, a number of loop iterations. I'm going to call it capital K. And the question is, how do I balance between choosing it too large, so there's not enough work to do for everybody, versus too small, so there's too much overhead? And so there are 4 variations. So let me tell you about the 4 variations. A fixed chunk size, how do you pick that optimally? And then various ways of picking varying chunk sizes over the course of the run. So here was the first paper in this business. It was a fixed chunk size. And what they assumed was that you knew the probability distribution of all of the task sizes, right? So this problem is only interesting if each loop iteration costs a different amount of time. Otherwise, it's sort of trivial. You give everybody one piece of all the work. But it's only interesting when they're all variables, so you have to know something about it. So what these people assumed is that they knew something about the probability distribution of all the task times. And there was an assumption which is called increasing failure rate. Let me say, if you plot the probability distribution, it decreased continuously, right? So the chance of long jobs kept getting smaller and smaller reasonably fast. And there's a technical term for that. And then they said, okay, so suppose I know this probability distribution, and I know it's, let's see, what do they need to know? They need to know its standard deviation, and we know the number of tasks, and we know the cost of scheduling, and how many processors there are. They gave an exact formula for how to prove how to pick the optimal task number of tasks to schedule, K. And so you chose the number of tasks, you divided by the standard deviation, you multiplied by the number of processors, you took the 2/3 power. They had some magic formula which minimized the total runtime with high probability. And so it's pretty mathematics, but it's not very useful in practice because you have to know this probability distribution, which is how likely is that to occur. And in a compiler, it makes sense because you have a loop, but this may not work in a general situation where you don't have it organized as a loop. Okay, so this was too much, too restrictive. So here's the next technique that people chose, which uses less information. It's called guided self-scheduling. And the intuition is very simple. At the beginning, you give out big chunks so that everybody has a lot of work to do. And then as you get near the end, you give people smaller and smaller chunks so that it balances out more nearly at the end. So at the beginning, there's not much overhead because everybody gets big chunks of work. And near the end, they're getting little chunks, so hopefully they all finish at about the same time. So the question is, when somebody comes to you and asks, give me a bunch of work, how much do you give them? And it turns out that the theoretical right thing to do is incredibly simple. You ask, how many tasks are left? I'll give you one piece of them. right? So at every step, you assume it's all going to be perfect. And of course, as you get closer to the end and there are not many tasks left, you give people smaller. So at the beginning, if I have 200 tasks and 10 processors, everybody's going to get a chunk of 20. But if there are only 20 tasks left near the end, everybody's only going to get 2, right? And so they'll all finish at about the same time. And that was another paper which does all of the theoretical analysis. So here's another variation on that theme that people did. In that case, Ki, that's the ith chunk that's handed out from the central queue on the ith request. It depends not only on how much work is left, but on some estimate of the variance, right? You don't know, so these tasks are not all the same size, but you have, you know the standard deviation of their runtimes. And so, and you can measure that because you know you can, over the course of the run, you don't have to know it ahead of time because when somebody comes back and finishes, they can report that information to you. So you get that information. And the idea is that if the tasks have a very high variance, if there can be very large ones and small ones, you should probably hand out less work, you know, fewer chunks on average because they could take a long time. But if they're low variance, if they're all really close to about the same size, then you should hand out more stuff. It should be closer to the, you know, the perfect amount, which is the total number left divided by p. And they gave, again, a formula depending on that standard deviation as to how to vary it. And they called that tapering. And that was a PhD thesis here a while ago. And so finally, there's one more variation on this business. And that took into account the fact that not every processor runs equally fast. So when somebody requests a task, it may be a CPU or a GPU, or it just may be, you know, some processors are shared and slower than other tasks. And so in that case, you just can throw weights into all these averages, where the weights are proportional to how fast each processor runs, and they change in a natural way to decide how much to hand out. And again, there's another more recent paper on how to do this and pick all the right numbers. Okay, so that's the 4 variations on this.
Quick question.
Yes?
The last one there, does that also incorporate the information about the variance and runtimes, or is that a separate piece?
I think this builds on all the previous stuff. So you can use the variance of the processor lengths and the variance of the processor speeds, of the task lengths and the processor speeds, because they're both varying, yes. So so all of this assumed that the tasks had no dependencies, right? So that's why people explored this particular variation quite a bit. So you can imagine one processor spawning a whole bunch of others. These are the loop iterations. The cost of each task was unknown, but maybe I knew the variance or something like that. I assumed locality was irrelevant, so I could just give them away to everybody. All I cared about was balancing it. These guys did not share data, which would have been important. And it was only made sense if I could centralize the queue so it only scales up to a limited way. I mean, it makes sense in a shared memory machine, but if I have to collect too much data, you know, if I had thousands of processors, the place where the central queue is would become a bottleneck. Anyway, but this is a good idea. Let me give you one system which has been quite successful, a software system that people have developed that uses this. It's called Cilk, and which I've mentioned earlier in the semester. Cilk is short for a language of the C ilk. So it looks just like C with a few language extensions. And it was developed by Charles Leisterson and his team over a number of years at MIT. And he had a startup company. It was acquired by Intel not so long ago. So this should be a standard tool on Intel platforms. And he has, you know, over time, people have implemented many, many different applications in it. But let me give you a tour of how you write code in it and how it does the dynamic load balancing. And so I will use a very, very slow implementation of computing Fibonacci numbers, so it all fits on one slide. This is the slowest possible way to compute a Fibonacci number. Use the fact that, the nth Fibonacci number is the sum of the n minus first and the n minus second. And so I will simply call this subroutine recursively and add the 2 previous Fibonacci numbers. And these 2 can, of course, be run in parallel. And of course, there's a closed form formula for the nth Fibonacci number. This actually costs fib of n to compute fib of n, which is bad, but it gives me lots of tasks to schedule in parallel. So this is the plain old C code. This is the Cilk code. I only had to add 4 keywords, all shown in red. So I put Cilk in front of it to let it know that it's a Cilk subroutine. And whenever I call this subroutine, I put the word spawn in front of it. So it sort of feels like p-threads. And then I have to wait for those both to be done, sync, and then I can add them. So this looks terribly slow because every time you do a spawn, you think I'm talking to another processor, but the runtime system is very smart. This doesn't cost any more than a subroutine call in C. All it does is it pushes it on the stack and it sits there. It runs equally fast. The only time you pay for it is if the work actually gets sent to another processor. Then there's some overhead, but as long as this is all running locally, there is no problem. So what this means is that Cilk any Cilk code will run, it's a superset of C. This will run on a sequential machine. Spawn does nothing. It will run at full speed. Everything just sits in the usual stack. And if you're on a parallel machine, it will automatically spread out the work. So there are no new data types or anything. So the semantics are all very familiar. So let's just ask ourselves what could be parallel here. And so let me just draw a picture of this thing running, and then I'll explain how it actually does divide up the work. So let me call fib of 4, which is small enough that it'll fit on this slide. And so the first thing I do here, so this is colored red. Let me get this. This should be color coordinated. Okay, so I call, this is colored purple because I'm calling that purple line there. And, okay, there we go. And so what that is going to do is call fib of 3, that'll be that line. And then it comes over here and it goes down to the next line, which is colored red. Okay. Those can both happen at the same time. So as I walk through this animation, let me do that again. That's the first time step. That's the second time step. So what can happen at the third time step, potentially, right, if I have enough processors? Then all of those are the next things that can happen. Fib of 3 will recursively call fib of 2. And this second line of code will also call fib of 2. So n minus 1 is 3, n minus 2 is 2. And that moves on. The next thing can happen all in parallel, or all of those lines of code. So again, in each of these is another call, these one of subroutines. So 2 calls 1 and moves on to 0. 3 calls 2, which calls 1. And then 2 calls 1 and moves on to 0. So I haven't done any returns yet. All of these arrows are kind of pointing down or sideways. So I have never yet gotten to this sync line where I could actually compute the sum and return something, right? So it's all going down the tree. So now it's going to come back up. And so what happens here, for example, is that this guy says, oh, my value is 1. I'm going to hit this line. I'm just going to return 1. So it returns that back. And so, but nothing happens yet because this guy is waiting. He's hit a sync, and he's waiting for 2 numbers to come back. Similarly, this is coming back. So in the next time step, finally I get to the return. So it's colored blue because that corresponds to this blue line of code. And so that return occurs, that return occurs. Then that return can occur. So it can only happen when the arrows say all the inputs are ready. And then finally the last step, that one occurs. So this all unfolds dynamically. It never builds the DAG. It all just happens in real time depending on where the stack are on every machine. So, and this will be, if I have enough processors, this will use all the processors, otherwise not. So the question is, how does this get assigned to different machines? And so let me tell you how fast you can hope to go, and then state the theorem that says Cilk actually attains this bound with high probability. So I'm going to let T sub p be the execution time to run the program on p processors. And so here is the DAG. So I'm going to assume it's there's no loops or anything. It's all just this call graph that goes down. And so there's the original call. And so T1 is the total number of nodes in this graph. That's the total amount of work. That's how long it would take on one processor. Just count the circles. And T infinity is how long it would take to run on an infinite number of processors if I had them. So let me do this color coding here. So if I have an infinite number of processors, how long it would take, I'd have to follow this chain. I'd have to follow this critical path from the first to the last. That would be T infinity. Can't go faster than that because there's sequential dependencies. So I get 2 lower bounds in the runtime of this algorithm. The first one is I can't go any faster than p times faster than 1. So the time on p processors is at least the time on 1 divided by p. But I also can't go any faster than the critical path. So Tp is at least T infinity. So the question is, how close can I get by doing scheduling cleverly in Cilk to get to as close as possible to the maximum of these 2 lower bounds? So let me just repeat what I said. So the speed up I'm going to be measuring is T1 over Tp. And that's never going to get better than P. If it's equal to P, it's called perfect linear speed up. These are familiar definitions, I hope. And we have seen superlinear speed up in some data that I've shown you before. That's if you have, for example, more cache because you have more processors, it could run faster. But in this simple model that we're using, you can't ever get superlinear speed up, right? Because I'm just sort of talking about how fast I can traverse that graph. And so now what I'm going to tell you is how Cilk actually does the scheduling, and then state a theorem that says how close it gets. So what we're going to do is greedy scheduling, and as soon as all of the inputs for a task are ready, it will be able to fire. So for example, at this, let's suppose I've gotten to a step in the code where I've finished all the orange nodes, and I want to know what can I do next. So the next two things that I can do are run the two red ones. They're the only ones that are ready to run at this point. I can't run that one because even though those two inputs are ready, that input is not ready. And similarly, this guy can't run, and this guy can't run. So I only have twofold parallelism at this point in the graph. So I can keep two processors busy. And so, but if I have p threads, if I have p of these red circles ready, I could use all of two processors. But if I have three, I'll call that an incomplete step because I can only keep two of them busy. Okay. So now, how does Cilk schedule? What it does is it does something called work stealing. So what it's going to do is that each processor is going to independently maintain its list of what it wants to do, right? It is traversing a part of this graph. So each processor has said, if I assign this to processor 1, it is working its way down. It's doing depth first. So it has part of this tree in its local stack. So each processor has a piece of the local stack. And what happens was, but let's suppose this processor has run out of work. So processor 2 has no more work to do. It needs to do something. What it's going to do is pick another processor at random and steal its work. So this is the list of work on P's stack. On P1s, there's P3 stack and P4s. It'll pick another random processor and steal something from it. So how's it going to decide what to steal? So this is a stack. The P is pushing stuff at this end and popping it off. That's how stacks work. What this is going to do is going to steal from the other end. It's going to take the oldest thing on the stack. And the idea is that this is sort of higher up in the tree, and it'll represent more work. So if this guy steals that, he'll hopefully not have to steal as much, because it'll be higher up in the call tree. Okay. So in this particular data structure where you can push and pop at this end and pop from that end is called a DEQ, a double-ended queue. That happens to be the name of the data structure. So this is pronounced DEQ for double-ended queue. So that's the algorithm. It's pretty simple now. And the question is, how well does it work? And the theorem, which is under certain assumptions, the time it takes to run that problem, where you have p processors, is bounded above by the perfect speed up time, the time it takes to run on one processor divided by p. We know we can't do better than that. Plus big O of the other lower bound, which is the time with an infinite number of processors. That's the length of the critical path. And so here is a very simple pseudo proof. It's not a real proof of why that's true. So the total amount of time that all the processors spend working is T1. So how can I keep them all busy? So I want to make sure I keep them all busy. So every time somebody has to steal something, what's the chance they grab something off the critical path? 1 out of p, right? Because one processor owns the point in the critical path, and so there's a chance of 1 out of p that will be stolen. So that means that the expected cost of all of those stealings from the critical path is p times the length of the critical path. Because I have to get the critical path that many times, and my chance of getting it once is t infinity over p. So, but I have p processors doing that, and so I'm going to divide that by p. And so the total time does turn out to be t infinity. Okay. So that tells us that on average we expect this to work. How much space does it take? Because there may be a lot of space overhead. And what they claim is that that's not very bad either. And let me just say what the picture is. Come down here. So let's suppose I have 3 processors. They're all sort of working on different parts of the total tree of the tasks. And let's suppose this processor has now grabbed that guy. This processor has grabbed that guy. How much space do they need in their local stack in order to do all the work? And the answer is, well, the only thing you ever have in the stack is bounded by the length from the top to the bottom. It's the total stack length of, from the top to the bottom. So suppose I ran this in one processor, and one processor executed this whole thing. Then how much memory would that one processor need? I claim the answer, S1, is just the depth of the stack, right? Because the way stacks work is it's depth-first search, and so I only ever need the length of the longest path. And if every processor is only working on a subset of this stack, they'll also only need that much space. So the total space grows proportionally to the number of processors, but one processor never needs any more space than a single processor. Okay, so that's Cilk, and it's available, and people use it. Let me now talk about some other tools. And I'm just going to give us a little survey. A lot of people have worked on what are called DAG scheduling software. DAG is the directed acyclic graph that everybody connects. Many people sort of slightly reinvent, explore the design space of how to do it. Here are a bunch of tools that I'll draw a few pictures of some of them. So the first library that was built for doing dense linear algebra was called Plasma by a colleague, Jack Dungera at the University of Tennessee. That built the entire DAG explicitly and then tried to optimally schedule it. That has its limits on how big it can be. I'll show you a picture on the next slide of how big these DAGs are. And so their next version of it was called Quark, where they only build a part of the DAG and sort of just the frontier. They so what is the next level of tasks at each part of it? I'll just try to schedule that dynamically. There's another project at university at the Barcelona Supercomputer Center. It's compiler based. So what you do is you take your code and you put in some annotations that say, here are the inputs, here are the outputs, you give them some names. And what the compiler does automatically is it says, oh, these inputs from this processor are the outputs of this. Let me say that again. The outputs of this subroutine are the inputs to this other subroutine. Therefore, there's an edge in the DAG from the one that produces them to the one that consumes them. It builds that for you automatically after you just label all your subroutine calls. And it builds that whole DAG and it schedules it for you. And so they've been working on that for quite a while. There's another version which used libraries instead of compiler technology that was done at INRIA. There's attempts to make, all of these were shared memory implementations. There's another group that's working on distributed memory, so to make it more scalable, so you can't have a centralized queue to make it all work. And then Intel has its own threading building blocks. Microsoft has its own tools. Lots of people are building these. So let me just show you what this is good for. And so let me show you two particular DAGs for the same mathematical problem optimized in two different ways. So here the problem is you take a symmetric matrix, you do Cilk on it, do the factorization, you invert the triangular factor, and you multiply the two inverse triangular factors together to invert the matrix. I'm inverting a symmetric positive definite matrix. So, and each of these little ovals is a task inside one of those three subroutines: factor, inverted triangle, and multiply two triangles. And so there's Cilk, there's invert, and there's multiply. And each one of these represents a little sub-block in the operation. So this guy at the top is the Cilk, the sequential Cilk of the top corner of the input matrix. And then after I do that, there's some matrix multiplies to update the rest. And all these edges indicate that finally I get done, and I do Cilk on the bottom corner, and I'm done. And then I do the next one and the next one. So that's one way of doing it. How many different, how long is this? So the time axis goes down. I can do that first. The next three can run in parallel. The next five can run in parallel. And altogether, if I've broken up my matrix into a certain number of blocks, let's say t by t, it's 7t minus 3 to get from there to there. Now, here is exactly the same set of operations, but I've now interleaved these three subroutines. So all of these tasks are the same, but these tasks don't have to wait for the very last one here to finish. Some of these can begin earlier. And the system is smart enough to understand that this guy could start, after that guy starts. And here's all of those tasks interleaved completely, and it's gone down by a factor of, from 7 times the number of blocks to 3 times the number of blocks. Of course, I need more processors to keep them all busy, but this is the sort of interleaving that can be done across subroutine boundaries, and that's done by this system. So here is what the architecture looks like of the system. This was done by Quark. The user has to modify the software by saying, here's a task, it's a subroutine, please insert it in the queue. So there's a few lines of code that you add, please insert this into a queue. And then the dependencies are computed for you. I think the user has to give some information so we know which tasks are created, and then it will, yes, please.
So on this slide and the previous one, I was wondering, so how much of this is sort of static and how much is dynamic? Is this all dynamic scheduling?
Yes, this is dynamic scheduling. Quark is done dynamically.
Okay. And it seems like a lot of these things, like the exact order might change depending on the data a lot. So,
yes, and how many cores you have available and who's busy and who's not. So this is one particular run that, that would work on a fixed number of processors. But it says the potential is a speed up by a factor of 7 to 3.
Okay, thanks.
Right, and so this is just sort of describing the infrastructure and how the code gets to vary. Okay, so here's what the API looks like. Here's the code that you would write. As usual, there's you have to start up Quark when you call your program, and you have to cancel it when you're done. But here's what the insert task looks like. This is the most of the work. You say, I want to call this particular function. It has some flags. I have to have some pointers to all of the inputs and all of the outputs, and I have to say which are which. And these are names which will then be used by Quark to make all the edges in the DAG. And then when you're done, you free everything. And it also has some barriers and canceling of tasks because that can occur too. Okay, so the question is, how does this schedule? How does this scale as it gets bigger and bigger? And so I think I mentioned this example before. We have the two options of build the DAG entirely ahead of time. If I have, if my problem is static, if I'm running Koleski, I couldn't potentially build the entire DAG ahead of time and schedule it. How many tasks would I have in it? Well, if I take my n by n matrix and break it up into b by b blocks and call a sequential subroutine for each of those b by b blocks, I'm going to be doing about n over b cubed blocks, and that's how many nodes are going to be in my graph. And so if I have a relatively modest-sized 10,000 by 10,000 matrix, that's not so big, and it's 100 by 100 blocks, they have to be about that size so the BLAs run fast on an individual block. I'll have 100 cubed or 1,000,000 of these vertices. And so that doesn't scale. And so let me now show you some performance numbers as I try this on a variety of different platforms and show you how well it works. So I'm going to show it to you from problems that are small enough that I can build the entire n over b cubed size DAG and schedule it perfectly. And I can always do better if I can build it and schedule it perfectly. And Quark does not. It just sort of does the frontier, builds a little bit of it and schedules it. And it can scale more, but let's see what the price is. So this is going to be some experiments on a 48-core Opteron, and I'll show you the experiments for 12, using 12, then 24, then 48 of the cores. And this is doing dense linear algebra, Gaussian elimination. And I'm breaking it up into lots of little blocks and scheduling it. The horizontal axis is the matrix size, up to 20,000 by 20,000. The vertical axis is gigaflop, so up is good. And I'm comparing the tuned code from Intel, that's MKL, that's blue. And then plasma is red, that's where you build the entire DAG and you schedule it. And then the green is Quark, where I don't build the entire DAG, and I just schedule dynamically. And so MKL does really well on 12 cores. It's winning. The other two, are okay, but they're close, but they're not quite good enough. But let's go to more cores and see what happens. So now I've gotten up to 24 cores, and MKL eventually still does better, but these two other tools are doing better when it's up to 10,000 by 10,000. They're keeping the processors busy. And finally, let's go to 48 cores, and now MKL is having trouble keeping up, and the other two are doing rather better. For this one, plasma, where I sort of have total information, it does go faster, but the other one, which is more scalable, gets within 10%. So this says that it's probably a reasonable idea to do the dynamic scheduling where I'm only doing the frontier of the DAG rather than the entire enormous thing. So the goal of this project is eventually to make Quark scale up to large distributed memory machines with thousands of processors. This is a very small experiment, but it does tell you it's a reasonable idea. So here's some future work for this particular project. It's all ongoing. So for plasma, so what I plotted here is how fast plasma goes. This is all very small. Let me make sure I'm comparing it. So plasma is blue, Quark is pink. the horizontal axis is the block size, the individual B by B blocks. And the vertical axis is performance, so up is good. And so you can see that both of them are rather sensitive to the size of the block. There's sort of a magic good number around 100. If you call a single task an 100 by 100 block, then it runs pretty fast. And so that's sort of the sweet spot, or 200, I should say. So as I said, the largest tests were for 48 cores, and they're working on building something that scales up to be larger. So let me just close this part with a picture of how well it's done the scheduling. So I'm going to show you a trace of how busy each processor was for the 48 core example for LU. And so here's a picture that comes out of some of the tools that you guys have heard about before. So there's 48 rows, one for each of the 48 cores, and the horizontal axis is time, and it's color-coded indicating which processor, what each processor is doing, what each core is doing. And so yellow is it's executing some subroutine and doing well. And they're all densely packed together at the beginning, so all the cores are pretty busy. And then at the end, they get sort of scattered out because that's what the dependency graph says, that there's not that much work to do. So maybe there's a better way to do the scheduling that would pack all these little yellow dots, and you could potentially save a little bit at the end. But in the middle, it does a pretty good job of packing them all together. OK. So that is everything I wanted to say about the sort of shared memory case, what people do. And I now want to move on to the distributed memory load balancing case. Any questions?
So one observation is everything we've said so far is for a single task you're trying to accomplish. So you're doing a single sort of problem. What happens when you start introducing multiple problems in parallel? How does this compose?
So if those problems are completely disconnected and embarrassingly parallel, then that's sort of a higher level recursive application of all this stuff. So if you told me that I had 10 different tasks and they all had different amounts of time, then I could sort of pre-allocate processors to them. Otherwise, I'd have to do this in some recursive fashion. And I'm not sure that I've seen, I think I will have some slides later that describe how to deal with something that is so large you don't want to write it all down and then do the whole thing at once. You want to handle it in a hierarchical fashion. I think that's the answer. OK. Yes?
For that Koleski example with Quark, would, given the same number of processors, would Cilk do pretty much the same thing and as well?
So I think that if you implemented each of these three subroutines independently in Cilk, with spawns and sinks, and as long as there was a global sink at the end of each subroutine, it would look like this, right? So it wouldn't be able to interleave it. You'd have to sort of write the code so that you wouldn't have this global sink at the end of each subroutine call in order for this interleaving to occur. And so that would be a rather major change to this. You have to rewrite all the software to sort of interleave all of these things. And this makes that unnecessary. You can write these three subroutines, and it will interleave them for you automatically, provided that you annotate it in the correct way with these particular kinds of annotations. I mean, so there's a fair amount of software infrastructure that needs to get built, but I understand how to do it in Quark. I don't see how I would do it in Cilk.
So along the same lines, in the load balancing community, are there any examples where someone has done, okay, we took our application and sort of did minor surgery to get it to work with Quark, and then we sort of, since we as the developers understand the structure of the problem, we did all the load balancing in our internal thing for our particular application, and then Quark does almost as well, kind of thing?
So most of the data is of the form comparing it to the best hand-tuned code, which is what is on this slide. Okay. And sometimes it does better than the best,
So MKL serves the purpose of that?
MKL has served that purpose. Or in the other, for example, you might compare against Scalapack. You might compare against, there are many different highly tuned implementations that one could in principle compare against. These are time-consuming experiments to do if the bottom line is always the best hand-tuned code, right? So the other, of course, metric is using a roofline model or some other simple theoretical model that says I'm getting this fraction of peak. So that's another way to do those experiments. Good question for class projects. Yes. Okay, so now let's get into the distributed case. And so we can't afford to have a single centralized global queue. And so what we're going to do is have a distributed queue. And it's not really a queue anymore. It's just sort of a bag, in other words, another technical term that people use. And so it's sort of a distributed data structure that lives across all the different processors. And you can access any part of it without touching the rest of it and grab something or put something into the bag. So when is this a good idea? And clearly this is, I'll show you how this gets implemented soon. It works on a distributed memory machine in a natural way. If there's a lot of synchronization overhead, you might want to use it in a shared memory machine too. It only really makes sense if locality is not important because things could land anywhere. And you could know the tasks in advance and they're all independent, or there could be dependencies, in which case they just get added to the bag whenever they're made available. Okay, so the question is how, and there are a lot of names that people have, this has been reinvented many times because it's a perfectly natural idea. I think there was even a design called Hungry Puppies. So just because people had to make up a new name that was cute. So what does each processor is going to do? How do you know when somebody comes to you and wants to steal your work, or how do you know when to go, who else to get? So you need to have a way to avoid deadlocks and waiting. And so here is a little state diagram that indicates how this is going to work. So if you're a busy processor, you're going to do a fixed amount of work, and then occasionally go check, is there a message waiting? Check your mailbox. And if you're an idle processor, you will randomly select another one and send a message, and then you'll go off and see if anybody has sent you a message saying, oh, I've got some work for you to do. So you need to have a sort of a state diagram here so that progress is always made, but you don't spend too much time waiting. So the question is, how do you select a donor? How do you select somebody to steal work from? And there are three basic techniques that people have tried, and they have different costs and benefits. So the first one is, I'll call asynchronous round robin. Every processor keeps a target. So it says, I'm going to ask processor target sub k for the next one. And after you've gotten the work from there, you'll simply go to target sub k plus 1. So everybody just loops around all of the processor numbers in order, doing mod the number of procs. And so everybody is asked. So now the other way to do it, but the trouble here is that it may be that one processor gets asked over and over again because these could all get out of synchronization. So you could also have a single centralized queue. Now that sounds bad, but if it's only keeping a processor number, then it's not so bad. So every processor will go to processor 0 and say, who's the next one I should ask? And so every processor gets asked an equal number of times. And then the one that people have had the most fun analyzing, and for which there's a lot of nice theorems, is you just do it randomly. You pick another processor at random, and you go ask it for work to do. And so that's the one that obviously scales the best. So I'll talk about that. So then the question becomes, how do I decide how big a task to put on the stack? And there's some obvious questions and trade-offs there. Do I put lots of little tasks on, a few big ones? But the other question is, when somebody comes and steals from me, what do I hand them? Because I have my own stack, I'm running, somebody comes and asks me for work, should I give them my oldest task, the thing that's the deepest down in the stack, or should I give them my most recent task? And that depends on the application, but what people often do is they're given the oldest task. That's the one higher up in the tree. It's more likely to have a lot of other children indicating work to do, and so that will minimize the number of requests for work. Okay, so let me tell you some of the theory that people have done. And there are two slides here, and the main result is in red, and it basically says, do the simple, obvious thing, pick somebody at random, and it's optimal with high probability. So the reason there's more than one result is that people make different assumptions about the dependencies among the tasks in order to prove this theorem. So the simplest one is, let's suppose I have independent and they're equal size tasks. And the algorithm is going to be, I simply take my tasks and I throw them into another random processor. So I have n balls and I throw them into n random bins. Right? So that's a very well understood probabilistic thing to do. So ideally, every processor would get one. But the question is, if I pick a random destination for every one of these n balls, how full is the fullest bin? How bad can the load balance be? And the theorem says that the busiest processor will have log n divided by log n, right? So that's how bad the load balance can be by that. Now, there's a very simple fix to make that exponentially better. What I'm going to do is not just pick one processor at random and throw it to them. I'm going to pick D processors, and each one of them I'll ask, how much work do you have? I'll pick the emptiest one of those D. And it goes down from log n to log n, divided by log D. So, and log n is constant for all practical purposes. So this is, it costs more, but because I have to have D communications, but it balances the load much better. And so the question is, of course, what do I do? What is the relationship between n, the number of tasks, and p, the number of processors? How many tasks do I need to have so that every processor is pretty busy, but if I do this random stuff? And the answer is I don't need that many more tasks and processors. Of course, I need at least I need at least p tasks to keep p processors busy. To keep it all load balanced, if I do this stuff, it turns out I only need p log p tasks, and then it'll be pretty well balanced by this randomized process. So that's the simplest case. So why are there more theorems? It's because people start saying, well, what if I have something harder than independent equal-sized tasks? So the next theorem, which is by Karp and Zhang, says that I'm going to assume there are actually dependencies now. So each task costs an equal amount, but they can be dependent on one another in an arbitrary tree. I don't know what the tree looks like. And all I know is that the parents must be done before children. The tree is going to unfold at runtime. I don't know what it looks like. And all I'm going to do is take my children and throw them into random processors. And the theorem is the same, that it all works, balances with high probability, no matter what this tree looks like. Okay? So, and so two more theorems in this direction. And the high-level bullet is the same. The simple idea works well. Just give them to somebody random. So when Lyserson was building Cilk, so here's the theorem that kind of justifies Cilk, they had a fixed task tree, but now the tasks had variable costs. But they didn't do it by picking a random task and pushing it there and throwing it. They did it by stealing instead. So that, I already talked about Cilk. They pick a random processor and they steal. So they proved that it's better to receive than to give. Is another way of describing what they did. And so you can sort of see why this works. Suppose there were, suppose there were one processor and it had all the work to do at the beginning. Then it should obviously push, because if everybody picks another random processor to grab work from and only one processor has work to do, then it's going to take a while for things to spread out. But nonetheless, despite that, they prove that stealing does the right thing. Okay. And finally, the last generalization, which was done at about the same time by a student here, they used a dynamic tree instead of a fixed task tree. And again, the task costs were variable. And so this works for branch and bound search, for example. And they did pushing instead of pulling. So their locality was worse, but it worked out well. Okay, so this was good for locality, right? When you steal it, then you tend to keep everything local until you absolutely have to go far away. And so this is better for locality. This is better for load balance, but it's worse for locality. Okay. And I'll just give you various references for this. There were a bunch of theses in the mid-90s on this, for doing this. Okay. So, question?
So all of this is for trees so far. Are we going to get any nice theoretical results for DAGs?
I think the next one might. I'm not sure. Ask the question again after I do the next few slides. And so this one is called diffusion-based load balancing. And all of the schemes I've told you about before, where I either pick somebody random to steal from or to give to, assumed everybody was connected to everybody. I didn't have to worry about how far away the processor was I was communicating with it. And of course, in real processors, real parallel machines, some processors are closer, cheaper to communicate with. And so what I'm going to do on those is take the machine topology into account and only do balancing with my near neighbors, the processors that are close to me. And so what I'm going to do, the simplest thing to imagine, is that I talk to all, let's suppose it's a 2D mesh, and I want to talk to my 4 neighbors. I will talk to my 4 neighbors, we'll all decide how much work we have, and we'll split it evenly among ourselves. Right? That is exactly the Poisson equation. So I sort of, I want to average with my nearest neighbors and say, how much work do I all have? I want to evenly divide that. And so this is called diffusion, because this is how physical things diffuse, right? Every little particle just sort of spreads itself out evenly to its nearest neighbors. And we've seen this, we've analyzed this to death. And so it's also called a Markov process, where you're sort of averaging with your nearest neighbors. And so this is, diffuses information more slowly. We've seen that picture before. If one processor in the middle of the grid has all the work and is only talking to his nearest neighbors, then the work will spread out slowly from the center, but it'll be cheap because you're only talking to your nearest neighbors. And there's lots of theory, you can imagine, we've seen a lot of it already, as to how fast this distributes work. And so you can take weights into account. Different amount of tasks have different amount of weights. There's a paper from SPA 96 for doing this. So one problem that they saw when they first did this is that work would slosh around. It would sort of move from one processor and then move back as it tried to get the load balance at each step. And so in order to avoid that extra sloshing in communication, they did something with, they made it a second order method which kind of slowed down the amount of work sent, but it kept things from oscillating. Okay. So any questions about this? Because I want to close with sort of the last system that is popular that people use that has many of these things built into it. And it has a cute name. It's called Charm++. And it was developed by Sanjay Kali at the University of Illinois. And it's been used for many different applications. And it's specifically designed for doing iterative applications where you're going to repeatedly execute a similar set of tasks. So think molecular dynamics, which is one of his original applications. So the molecule changes slowly, and you're gathering data to compute forces, and it happens over and over again. So that means you can afford to do the load balancing in an expensive way occasionally, and only once in a while have to update it. So it's a runtime system, and you're going to you have to annotate your code. You're going to decompose your work into chunks, and you might over decompose it to have lots of little ones. And it's going to migrate the chunks for balancing the loads. And it's going to, so how is it going to do this? It's going to have this, it could rely on the user providing information, but instead the runtime system is going to collect the statistics for you. And as soon as it gets enough statistics, it'll decide that it's time to do some load balancing. Okay. So it's going to collect both the communication patterns, statistics over time, and the computational loads. And so it's going to assume that there could be abrupt changes, but they're not going to happen very often. Or they could be slow and small changes. It'll deal with either flavor. And so it will, the runtime system takes care of this all for you, and it's going to assume the recent past is a good predictor of the near future. So, oops. There we go. Go forward. So let me sort of skip ahead to a picture of what this is going to do. So here's sort of a timeline of what will happen. So here, the horizontal axis is time. It's sort of color-coded by what's going on in the system. And the yellow are sort of regular time steps. And so at the beginning, it's going to run for a while. And then the system will do some instrumentation. We'll switch on and collect information about what you've been running. And we've seen this in POSCI. When you call POSCI, it sort of keeps track of what you've been doing. This does it in a much more general case. And then once it's collected some information, it'll spend a little while doing some complicated load balancing in the hope that it'll do it once and you'll get to reuse it. And then it'll do some instrumentation and see if it's done a good job. It may update it a little bit. And then, hopefully for a very long time, it will now just do your work, and it'll be very well load balanced for a while. And then it'll maybe have to instrument again, maybe update it slightly, and then it'll go back to doing regular work for you. So there are two challenges for doing this, and because his goal in particular is to make it scale up to arbitrarily large machines. So the question is, how do you get all this information and collect it without bringing it into one place and still do a good job of load balancing? Because you still have to take into account, and he also wants to take into account the interconnect topology. So this is the hierarchical stuff that somebody had asked about before. So what I'm going to do is do load balancing locally, and then go up a tree, and the parent is going to take a summary of how well its children are load balanced, and load balance among siblings. So here is, if you like, a tree. And at the very beginning, what each local part of the tree is going to do is I'm just going to load balance among that subtree. So the idea is that these are tasks, but they're located all on one part of the machine. So let's say one corner of a 2D mesh, and that's another corner of a 2D mesh. And so these will communicate among one another, and they'll do as good a job at load balancing as they can. But it still may be that this is, let's say, the northwest corner of my grid, this is the southeast corner, and this may be load balanced, but altogether this has a lot more work than that. So the whole thing is not load balanced. How do you fix that? Well, once these guys are all load balanced, and what they will do is send their total amount of work up to the parent. And then the parent will check, are all of my 4 children load balanced in a hierarchical sense? And if not, the parent will help the children and send a message back down that says, please send some stuff from this child over to that child because these children are hungrier than that one. Right? So it'll work its way up from the leaves to the root, and at each level you don't have to send up too much information to do the load balancing. So that's how it tries to scale as opposed to having the parent know everything. Okay. Too many animations here. Okay, finally. So it tries to do this, I've already said this, in a topology-aware way. And so if you have a torus network, and his target has been torus networks, in this picture that I showed you before, indeed, these are subtori. So this may be one corner of your mesh, another corner of the mesh. So when these guys are load balancing among one another, they're not using any of the same edges in the communication network that this guy does. They're all disjoint. It's only when you go up to a parent that some sharing has to take place. But most of the work is going to happen down here, and that's what it is on a torus network. So we're only going to do communicating of nearby objects, and hopefully that will do most of the load balancing. Okay, so finally I will close this with some data, some pictures of what it looks like. And so here is a molecular dynamics simulation called NAMD. That's one of their main applications. The horizontal axis is the number of cores they're running on. The vertical axis is the time, so down is good. And here they did load balancing in several different ways where they didn't pay any attention to the topology versus 2 different topology-aware ones. And the point is that this one keeps scaling much better and gets all the way down to, scales almost perfectly down to up to 16,000 cores, whereas this one sort of gives up around 4,000 because it wasn't aware of the topology. Okay, so finally, let me close with a sort of summary of the lecture. So all of these algorithms, there was a trade-off between locality and load balance. If locality is most important, then I may not be able to load balance everything perfectly. But if I don't care about that and I can spread out the work evenly without worrying about communication, well, then I can do that instead. People have been working on this problem for a long time, and that's why I try to give you a survey of papers that go back to the 80s of ideas, hopefully one copy of each idea, even though many of them get reinvented. And there were different solutions depending on whether you had shared or distributed memory machines, depending on the dependencies, the task cost, what communication cost. And so, and also when you know the information, do you know it ahead of time? Is it completely dynamic, or do you know a little, does it evolve slowly? And there are lots and lots of tools, and so please don't reinvent the tools, just use them when they're available. And so let me close with an open question, which is that all of this was originally invented to deal with irregular problems on irregular machines. So the question is, will future architectures make this necessary even for what we think are totally regular problems? And so let me give you an example. This was a paper at a supercomputer conference not so long ago. They were running on a completely homogeneous distributed memory machine some totally regular operation, and it was terribly load balanced. And using all these tools, it took a long time to track it down. And the reason that it was terribly load balanced is that there was a operating system daemon that every once in a while popped up on every 16th core and did something for a while, and just totally, in which they had no idea was going to happen, and it took them a long time to figure that out. So they fixed that, but you can imagine this is going to get harder and harder to discover on machines. Machines are going to run at different speeds, even though they are allegedly homogeneous, because there are going to be failures that take longer to recover from. Parts of the machine are going to be shared, and so the network is going to have different speeds. So maybe we're going to have to use all these techniques for what we used to think were totally regular things that we could just do by hand. So maybe that's the future. And I'll stop there.